So the point of our project is to evaluate whether we can learn the game Connect 4 using handcrafted feature vectors rather than the entire state. We also wanted to test learning this game on a online algorithm. So we did this with true online Sarsa Lambda because it would offer us the greatest control between one-step methods and Monte Carlo methods. Before we talk about our general results, let's go over each of the files. Game.py is our code base for just the Connect 4 and game in general. Agent.py includes each of our agents. Sarsa feature agent includes all of our handcrafted features that we use in the feature vector. Alpha beta is the agent that we use to train against. There's also a human agent and a random agent. Sarsa Lambda includes all of the code for the true online Sarsa Lambda function. And lastly, runtime.python notebook is a file in which we run the Sarsa Lambda function with different parameters and then collect and graph results and evaluate performance.
While the majority of previous reinforcement learning solutions to Connect 4 uses the entire state space of Connect 4 in their models, we hope to find a computationally more efficient solution relying on a simpler representation of the board. Features that we found useful to extract from the game state include binary values indicating which columns an opponent can win in with their next move, binary values for which columns the agent can win in with their next move, and which columns that placing a piece in would enable an opponent to win with their next move. The intuition behind these selections being that they give the agent strong indicators of high priority moves, avoiding a loss or winning the game.
We also included features that convey the number of pieces belonging to either an opponent or your own pieces in each column. This gives the agent a general idea of who has dominance over what areas of the board, and is just meant to guide behavior until the other three aforementioned features can kick in, because those features are not really activated towards the end of the episode. So we needed a feature to guide behavior until those features could actually work.
To train our reinforcement learning agent, we have it play against an alpha beta agent that searches up to a depth of 2 moves. We were unfortunately limited by the computational intensity arising from the exponential nature of deeper alpha beta searches to this 2 depth limit.
An interesting caveat about Connect 4 is how each state has an equivalent state. This means that in the case of Connect 4, this means that moving in column 0 is the same as moving in column 6. What this enables to do is essentially learn off of 2 games at once. So if a game is playing out mostly on the left side of the board, we can also learn on the equivalent game playing out on the right side of the board. To do this, we implemented an altered version of true online Sarsa Lambda that learns off of both games at once.
After training an agent with differing trace decay values and comparing the performance of the resultant weights during evaluation, it became glaringly obvious that methods with trace decay values closer to 1, and thus those approaching the Monte Carlo method, vastly outperformed lower and 0 trace decay values.
We deduce this to be caused by the nature of the reward signal in our Connect 4 environment, because the agents only realize rewards at the terminal state according to our rules. The agent is predisposed to working towards as Lambda reaches 1.0, which is Monte Carlo methods.
In the end, an agent trained with a trace decay value of 1, effectively a Monte Carlo algorithm, performed the best, winning all 1,000 evaluation games against an alpha beta agent that randomly chose between depth 1 and depth 2 searches, thus providing some variability in our evaluation games. We came to 3 conclusions during our research. The first being that the Monte Carlo approach is more effective when reward signals are only at the end of the episode, such as in our game environment.
So, and 2, that our feature selections were at least somewhat successful in learning Connect 4, as our agent, when it was trained with effective hyperparameters, was able to beat a 1 and 2 ply alpha beta opponent. Furthermore, when playing it against a human opponent, We saw optimal behaviors like starting optimal or playing at optimal starting locations, setting up wins and blocking up wins. And three, our adaptation of true online Sarsa Lambda for games with equivalent states could potentially work on other games that hold the same property as Connect 4 with equivalent states.